we were discussing about, you were discussing about Hamiltonian problem, right? Hamiltonian cycle problem. So, we will see a generalization of that problem. Okay. So, Hamiltonian cycle problem is only a yes or no question, right? Given a graph, does it have a Hamiltonian cycle or not? So, there is no approximation there, right? It is always a yes or no, right? But today we will look at a problem which is a kind of a weighted version of the same problem called traveling salesperson problem. So, before we begin, you are doing this, right? So, can you give me an example of a graph in which every vertex has even degree and every vertex lies in some cycle, still the graph does not have any Hamiltonian cycle? Okay, there are examples. So, suppose you know what a cut vertex is? Can you draw a graph without a cut vertex, even a cut vertex? Without a cut vertex also. Biconnected, that is, even if you remove one vertex, the graph will not become. This is only to brush up, nothing very much important to this, but okay, you can get no cut vertices also. Still, can you get? Anyway, Hamiltonian cycle problem is difficult. If you could check it only by checking all these conditions, then it would have been very easy, right? Right. So, you should definitely have many examples. So, can you? So, anybody who was not present in the previous session? Okay. So, you know what a Hamiltonian cycle is? Okay. You got it? Okay. Those vertices have got degree 3, degree 4. So, it is okay, it is okay. So, there are many examples like this. I just asked what he drew is this one. There are many such things possible. This one, no? Okay. Okay. So, this one you can convince yourself that this does not have, every vertex has even degree, not cut vertices till there is no Hamiltonian cycle. So, these simple conditions anyway will not help you to check whether you can eliminate. If a graph has degree odd or degree only 1, then you cannot get it certainly, right. So, such things are easy. Cycle. I am not talking about path. Now, we are thinking about only Hamiltonian cycles. That is a cycle that is in the graph that starts from, that visits every vertex exactly once. Okay. So, a traveling salesperson problem is just a generalization of this. So, in the application world, it is stated as, say, suppose you are given a weighted undirected graph. So, you are given a graph G and a weight is on the edges. So, W is a function from set of edges to say rationals, okay, and you need to find a circuit, that is a cycle in this graph which visits all vertices, that is it is a Hamiltonian cycle, but of the minimum possible total cost. That is the, if you sum up the weight of the edges that you are traversing in the Hamiltonian cycle, every edge has got some weight, the total weight should be as minimum as possible if the graph has multiple Hamiltonian cycles. Okay. If the graph does not have any Hamiltonian cycle, you can return infinity, right. Given a graph, if it has a Hamiltonian cycle, then return one with minimum cost, minimum weight. So, problem is does decision version is given a graph G and a K, does there exist a Hamiltonian cycle in this graph which is of cost at most K. The optimization version is find a Hamiltonian cycle in G of minimum possible cost, possible total cost is sum of weights of edges in your cycle. Okay. That is how the cost is defined. So, this problem can have, we can think of approximation algorithms, right, because this is an optimization problem. You can say if the graph has a Hamiltonian cycle of say total cost k, can you find a Hamiltonian cycle in that graph with cost at most 2k, right? That will be a 2 approximation, right? Given any graph, can you do that, right? Hamiltonian cycle does not have that, but TSP has, right? But the interesting thing about this problem is that you can show in fact that this problem cannot have any approximation algorithms at all. It is not possible unless P is equal to NP. Forget about 2 factor, 4 factor, even log n factor. We saw approximation for set cover in the factor was log n, right, where n is the number of elements, right, or we saw another one in which f was the factor. Those were not very good as compared to 2 or anything, but this one, even that log n kind of things are not possible. Nothing is possible basically. See, the cost here is not necessarily like 1 or 2. It can be, the edge cost can be even like n to n anything, right. So, the total cost can be much higher. So, that is why I can even say that there is not even an n factor approximation possible. Okay. So, our first agenda is to show that, so there are problems for which it is not only that the problem is NP hard. So, we will think, okay, let us try for approximation algorithms, even that cannot be done unless P is equal to NP, right. And say there are problems like say vertex cover, we saw a 2 approximation, right. Nobody has found a better approximation algorithm for vertex cover so far. We saw many methods to get 2 approximation, right. So, it is believed that under certain assumptions, it is known that for minimum vertex cover, there is no say like 1.25 or something, okay. So, unless P is equal to NP, which we believe is the mean P is not equal to NP, that is what we believe. Under that assumption, it is actually known that the minimum vertex cover problem cannot have a approximation with factor less than 1.25 or something. Okay. Forget about that number, which is something like this. Okay. If you want to show there is no 2-factor approximation possible for minimum vertex cover, then this assumption has to be not P is equal to NP, but P not equal to NP, but something stronger. Okay. But all these are very difficult to show, or what you say, it needs additional machinery to show that such hardness results are there. That is, these problems are hard to approximate below what we know, right? It is difficult to show. Not saying it is not possible or anything, but you need additional machinery. But this problem, one nice thing is, it is very easy to show that no approximation at all is possible for this problem. Okay? You got the ground where we are standing? Okay. So, let us now come back to this problem. So, can you first show me a reduction from, it need not be about approximation hardness, from TSP from Hamiltonian problem to TSP problem. Can you show it? That is, first to show that TSP problem is NP hard. Decision problem, okay, decision problem. Then later we will show that it is even hard to approximate. So, you can reduce it from the related problem, right, which is Hamiltonian cycle problem. So, show this. What is the reduction? So, what is the input? Hamiltonian cycle decision problem, graph G. That is all, right. And what about this side, what do you want? G and integer k, or some other graph, right. Say, let us say G dash and k, such that you want to ask if G has a TSP or Hamiltonian cycle of cost at most k, right. Okay, you are saying let us say G dash equal to G, but I need to also give weights, right. It is not only that this graph is okay, this is a graph without weights, okay. So, you have to give that also, right. G dash is G itself, but what is W? That is V of G dash is V of G, E of G dash is E of G, what is W of G dash? What property should the reduction satisfy? That if there is a, you have to also tell me what K is. K can be taken as the number of vertices. Okay, let us see. Okay, K is number of vertices. Okay. Now you only need to tell me what are the edge weights. One for every edge.
If there exists an edge. If there exists an edge, then
okay. So, does that correspond? Can you show that if the original graph has a Hamiltonian cycle, then this graph will have a Hamiltonian cycle of total weight n? Yes, right? Because a Hamiltonian cycle will have exactly n edges, and that is true. The other way, if you can find a Hamiltonian cycle of weight n in that new graph, which is the original graph itself, you certainly can say that there exists a Hamiltonian cycle in that graph, right? So, the reduction is trivial, right? Okay. Huh? Number of vertices, right? Because you want to visit all of them only once, right? Yeah. Cycle will have only n edges. Okay. So, that is the reduction. Now, instead of taking the second graph as G itself, I can also take it as a complete graph. Okay? And then I will tell you, okay, for these edges, okay, you retain the weights as 1. And for other edges, if you make it 0, then the cost is going to go low, right? So, for other edges, you put something bigger so that we can still distinguish. Okay? So, that is another reduction possible. So, we are given a G. Okay. From that, if it has n vertices, you will compute a Kn. I mean, this is your new graph. N is the number of vertices in the original graph, and you have this small k, which is the weight of the cycle which you want to find. So, that will be, you can retain it the same, it is n, right. You want to check if the second thing has a cycle of weight n, so that you will get an answer for Hamiltonian cycle in the original graph. So, let us say k is equal to n. Okay. And then for, I already told you, for edges that are present in G, assign weight equal to 1, W weight of the edge. For other edges, what do you do? Let us then just put 2 for every other edge, right, of Kn that is not present in G. Let us put 2, then see what happens. For every other edge E, weight of E is 2. Okay. So, this is our assignment. Will the reduction still work? True, right? Because if we are taking any of the edges of weight 2 to complete our cycle, then the cost required will be more than n, right? We cannot find it within n, right? If the original graph has a Hamiltonian cycle, you will get a Hamiltonian cycle in the new graph of cost n. On the other hand, if you have a Hamiltonian cycle in the new graph of cost n, it means that none of the edges in that Hamiltonian cycle has weight 2, right? If there is at least one weight 2 edge, then cost will be at least n plus 1, right? So, you can, the both sides it works, right? So, that is also a valid reduction, right? Now, I want to slightly change this reduction also. I want to say that I want to conclude that Hamiltonian cycle problem has no two-factor approximation. So, even if I could find a two-factor approximation for, I mean TSP has no two-factor approximation, that is what I want to conclude. So, you have to give me the weights in such a way that even if I I need not exactly find a minimum TSP in the resultant graph, but suppose I could find even a 2-factor approximation of a minimum TSP in G dash Kn. Okay. Still, I will be able to get a Hamiltonian cycle in the original graph. So, what does that, what will be the result of this? What I am asking you now is, give me a reduction from Hamiltonian cycle to TSP such that if I knew a 2-factor approximation algorithm, polynomial time 2-factor approximation algorithm for TSP, I can solve the Hamiltonian cycle problem precisely, exactly. Okay. So, what is the conclusion? If you are able to give me this, then what can we conclude? Okay, if I could find a 2-factor approximation for Hamiltonian TSP, I can find Hamiltonian cycle exactly in polynomial time, which is not possible unless P is equal to NP, right? So, unless P is equal to NP, if you can give me a reduction like this, it will mean that unless P is equal to NP, what is the conclusion? Unless P is equal to NP, what can you say about the approximability of TSP? There is no such 2-factor approximation possible for TSP will be the conclusion, if we can find a reduction like this. Do you agree with that? My claim is, suppose you can give me a reduction from Hamiltonian cycle to TSP, okay, this kind of a reduction such that even a 2 approximation for TSP will give me a precise answer for this, right, in polynomial time, which is not possible unless P is equal to NP, right. So, the conclusion is that such a thing will not be possible. So, the gap, the missing step is now to find a reduction such that even if I do this approximately for TSP, I can precisely answer Hamiltonian cycle in polynomial time. Okay. So, can you modify the reduction and tell me how this can be done? So, what I told is, from this I can conclude that unless P is equal to NP, a 2-factor approximation algorithm poly time for TSP does not exist. That is what we concluded. So, give me a reduction. Modify the reduction, modify the edge weights. what should be the, earlier I had put 2, can you do something else? For the non edges I had put 2, right, edge weight 2. You should have a larger gap between a yes instance and a no instance basically. If there is a Hamiltonian cycle in the original graph, the resultant graph should have a Hamiltonian cycle of weight n, and if it does not have, the original graph does not have, then within 2 factor of that n is like 2n, right, should be more than 2n. The total weight of the cycle should be at least 2n plus 1. If you do that, then this is done, right? Not sure? So, okay. So, I am going to give you some more clues for this, okay. Suppose you could see one difference between finding a hardness and finding a algorithm is that one is creative, the other is I mean it's construction, right, algorithm, but this is not construction, this is almost like creating a contradiction, right. So, that is probably the difficulty that you have. Suppose you could find a reduction where if G has a Hamiltonian cycle, then the new graph, the reduction instance has a TSP of size of cost n, and if G has no Hamiltonian cycle, let us say G dash, okay, then G dash has no TSP of cost less than or equal to 2n. Okay. Suppose I am able to produce this kind of a gap. Okay. If the original graph has a TSP of cost n, then I will get Hamiltonian cycle, then I will get a TSP of cost n. If the original graph did not have a Hamiltonian cycle, then not only that I do not have a TSP of cost n, I do not have n plus 1, n plus 2 or anything in between n and 2n also. There is a gap between the original instances, original problems yes instance and no instance creates a wider gap in the cost possible in the resultant graph. Okay. So, suppose I could do a reduction like this, then can I make this conclusion that, okay, suppose I could do a reduction like this, okay, then think of this that I could solve the TSP problem with approximation factor 2. Okay. So, that means if the new instance has a TSP of cost n, what will the approximation algorithm do?
2 times n.
So, it will definitely find me, if at all it has a cost n Hamiltonian cycle, my approximation algorithm for TSP will find me some Hamiltonian cycle of cost at most 2n, right. So, if it finds some TSP of cost at most 2n, I will say yes for the Hamiltonian cycle, right? Right? Run your TSP algorithm, two-factor approximation algorithm on the reduced instance. Okay? It is a two-factor algorithm. If this graph has a Hamiltonian cycle of cost n, it will give you one Hamiltonian cycle of cost at most 2n, in which case TSP of cost at most 2n, right? Let us call it Hamiltonian cycle of cost at most 2n. Then you can say yes for the original. Okay? Isn't it? Because, okay, so suppose we run two-factor, suppose there exists a two-factor algorithm and we run it for TSP on the reduced instance on G dash. If it finds a TSP of cost less than or equal to 2n, say yes. Say yes for the Hamiltonian cycle problem. G has a Hamiltonian cycle. Otherwise, if it does not find any TSP of cost less than or equal to 2n, then G has no Hamiltonian cycle. Is it true? Think about it. It's not that difficult. I have not shown you any reduction as yet. I am just telling you what will be the consequences of the reduction. Suppose you had a reduction and suppose you had also a polynomial time two-factor approximation algorithm for TSP. Then you can use this algorithm, right? Use this algorithm and solve TSP on the reduced instance, which is Kn, right? So, in this graph, if it is telling you, okay, there is a TSP of cost at most 2n. If it had a TSP of cost n, it will at least find a TSP of cost at most 2n, right? If the graph, reduced graph G dash has a TSP of cost n, it may not find that, but it will find at least one with a cost of less than or equal to 2n, right? Then you can say yes for the original, because my assumption is that suppose G has no Hamiltonian cycle, then G dash cannot even have a Hamiltonian cycle of cost less than or equal to 2n. So, I can safely say yes. Fine? Okay. The minimum, if at all the original graph did not have, then the cost of the minimum Hamiltonian cycle in the minimum TSP in the second one will be 2n plus 1. So, our algorithm cannot anyway find that, right? If it is not there, it cannot return that. That is why. So, otherwise, if this approximation algorithm is not giving us any TSP of cost 2n or less, you can say no, right? It is finding something, so that means it is within two-factor of the optimum. So, at least half the cost of that there should be a Hamiltonian cycle, right, which is not there anyway. I mean, that is not a Hamiltonian cycle in the original graph. Just think about it and ask me if you did not understand. Okay. So, this is the conclusion. If you are stuck somewhere, ask where you are stuck, why, what you did not understand, otherwise I will have to assume that you understood. Okay. So, what I am telling you is, what we want to conclude is that G has, we can find an exact solution for Hamiltonian cycle in polynomial time if we could find a two-factor approximation for TSP which runs in polynomial time. So, that is which is not possible unless P is equal to NP. So, that will give us the conclusion that such a two-factor approximation cannot exist. That is where we are starting with. Okay. Now, so we have to find a reduction where if I can find solve TSP approximately, I can solve HAM exactly, right. So, I am telling you this, I did not tell you what this reduction is, but I am telling you your aim for the reduction is this, objective of the reduction is this, something like this. In such a way that you reduce such a way that if the original graph has a Hamiltonian cycle, you will get a TSP in the resultant graph of cost n, okay. And if the original graph has no Hamiltonian cycle, the resultant graph does not even have a TSP of cost 2n or less. It can have only greater than 2n, okay. Your task is to find such a reduction first in the first place, okay. Suppose somehow you did it, then can I say that now if I had that two-factor approximation, then I could solve HAM exactly, HAM cycle? Yes, because this kind of a reduction you are getting, okay. You somehow know how to derive it, somebody is giving you, telling you how to do it, or you found out, okay. Now, you also, for contradiction, assume that you have a two-factor approximation algorithm for TSP. So, what will you do? You will run this TSP algorithm on the reduced instance, right. So, if that graph, okay, so if G had a Hamiltonian cycle, then G dash has a TSP of cost n, and the approximation algorithm will give you a TSP in the reduced graph of cost at most 2n, right. So, you can say yes. My decision is this, if you get a cost of less than or equal to 2n in the resultant graph, say yes, otherwise say no for Hamiltonian. So, that is correct because if G has a Hamiltonian cycle, then G dash has a TSP of cost n, and my algorithm will certainly find something of cost less than or equal to 2n. So, my answer is correct, right, in the yes case. Now, suppose my answer is no, even then it should be correct, right. If my answer is no, I am saying if it did not find a Hamiltonian cycle of less TSP of cost less than or equal to 2n, then you are sure that that graph does not have a Hamiltonian cycle of cost less than n, right, less than or equal to n, otherwise it would have found, correct. So, if the graph does not have a Hamiltonian cycle of cost n, then G also does not have a Hamiltonian cycle at all, right. That is what this kind of a reduction will give you. If you did not get less than 2n, less than or equal to 2n in the new graph, you are sure that it may have something like 2n minus 1 and all, it may have, but less than or equal to n it cannot have the new graph, because if less than or equal to n were there, you would have found at least 2n, right. So, that means G dash does not have in fact anything which is less than or equal to n, right. So, that means that what did I say? If G had a Hamiltonian cycle, you would have got. So, that conclusion is that G does not have a Hamiltonian cycle of size, a Hamiltonian cycle. So, your answer is yes, correct even in that case. So, that is the proof. Is it fine now? Okay. Just think about it once more. So, if you want a full thing, G has a Ham cycle. Then G dash has a TSP of cost n. Algorithm will find one with cost less than or equal to 2n. So, my answer is yes, which is correct. I should answer yes if G has a Hamiltonian cycle, right? If G has no Hamiltonian cycle, G dash has no TSP of cost less than or equal to 2n. So, even if our approximation algorithm is run, the algo returns a TSP of cost greater than 2n. If it returns something of cost greater than 2n, this implies that G dash has no TSP of cost less than n, less than or equal to n. If it had, then algorithm will return less than or equal to 2n, right? Something of cost less than or equal to 2n. So, if G dash has no TSP of cost less than or equal to n, it means G has no Hamiltonian cycle, right? This implies that G has no Ham cycle. So, that is the entire proof. If you now everything is there on the board. Even in this case, our answer is correct. Right? My answer is like this. If I find something less than 2n, say yes, otherwise say no. Answer is correct in both cases. Fine? Are you convinced? Fine? Not fine? Fine? Okay. So, now your task is to find such a reduction. Assign edge cost such that this conclusion holds. So, what should be the edge weights for the other edges? N plus, anything bigger, I think it should be 2n something, right? Yeah, n is already there, then another n plus 2 is sufficient. But it is easy if you just give 2n. Okay. Okay. Just, right? So, the reduction is simple. For every edge that is present in the original graph, give cost 1. For all other edges, give cost not 2, 2n. So that if at all you are including any of these new edges, you will have cost at least 2n plus 1. He told actually 2n is not required, it can be slightly less also, because all other edges will together give you at least n minus 1 plus, right. So, this reduction I am giving you now. if E is an edge of G, weight of that edge is 1 in G dash. E does not belong to E of G. Weight of E is 2n. Okay? Then it satisfies our requirement, right? Fine. If G had Hamiltonian cycle, you will get a TSP of weight exactly n. Otherwise, you will get a at least 2n plus 1, right? Then that is done. So this is 2 factor is not possible. Now suppose I want to say tell you that 3 factor is not possible. Then what will you do? Just give 3n for the other edges, right? Suppose I want to tell you that there is no log n factor approximation algorithm possible. You can give n log n, right? N log n. So suppose anything, right? Anything that you tell me, prove me that there is no alpha n factor approximation algorithm. Alpha of n is a function. Suppose alpha of n is any function. I will tell you, okay, for the non edges you just put alpha of n times n as the weight. Then it will tell you that even that is not possible, right? Okay. So that is the reduction. So instead of this, if you want to conclude that, if you want to conclude that an alpha of n is a function factor approximation is not possible for TSP, assign weight alpha of n into n for non edges. And weight 1 for edges of G. Okay? That is sufficient. The same argument you can repeat and it will tell you that even an alpha n log n is not possible, n is not possible. So alpha n for any computable function alpha. Any polynomial time computable function. This is, I am saying polynomial time computable function alpha because you need to give that weight to edges, right? The reduction should run in polynomial time, that is why. Okay? N square, everything is polynomial time computable. 2 power n is also polynomial time computable, right? Why? It's a value, right? If you multiply 2 many times, you will get it, no? Take 2 power 2, again multiply both, then you will get 2 power 4. Okay. Or it is just a number with 1 and all other zeros, right? In binary. So it's not difficult. Okay. So this part is done. So this problem is very hard under the assumption that P is not equal to NP. If you assume that, then you can not find any approximation algorithm, practically any approximation algorithm for TSP problem. So TSP problem is much harder than vertex cover or any set cover, anything like that in terms of approximability. Okay. So what do you do? But TSP, if you remember, this comes in many applications, right? So suppose a postman wants to visit all the, it is traveling salesperson. So traveling salesperson wants to visit all the cities. He wants to sell something, but he does not want to go through the same city more than once. He wants to visit all places and come back to where he started. So, this is a TSP instance, right. So, there are many instances where this problem you actually want to solve. Okay. So, and it is very hard. So, you cannot even approximate. So, what do you do? So, let us see if there are some cases, some restricted cases where this problem can be at least approximated. Okay. So, one such instance is where we have some property on the weights called a metric property. Okay. So, that is what we are going to do now. Suppose the weights cannot be like this, say some weight is 1, another weight is 2n, that kind of difference is not there, but the weights satisfy the property that assume that the graph is connected and all that, okay. It does not spoil anything, otherwise we do not have Hamiltonian cycle anyway. So, let G be any graph, any connected graph, okay. If for every edge UV we have for any 3 vertices, okay, weight of UV, the weight of the edge UV is less than or equal to the weight of going from U to say W, then from W to V. So, this is triangular inequality, okay. So, suppose for any triple of vertices, the direct edge between U and V has weight less than or equal to the weight of going to first something else and then, okay. So, if this is the case, then we say that it has metric property. So, can this graph be anything or my claim is that it should be a complete graph. If this is the case, then all edges should be present. Can you see why? It is not just a graph with this property, all edges should be there. If at all some edges, it is a connected graph, some edges are there, right, already. Then all edges should be there. Why?
Because if one is not there, then it will be infinity. Like if 2 vertices don't have an edge between them, then this equality will fail.
But how will you come back to this one? Maybe that other edge is also not there. Right? You should have the other 2 to argue that this should be less. Why should you have the other 2? So, can I say this? Suppose P is a path between U and V, okay, in G. It is there, right? for every pair of edges there is at least one path between them because the graph is connected, right. So, let us take this path. Let us call these vertices as intermediate vertices as V1, V2 to say Vn minus 1. This is our V0, this is Vn, okay. Rename, okay. Think of them like this. So, what the triangular inequality tells you is that if this is W1, this is W2 to Wn, the distance, the weight of the edge between this u and V2 should be less than or equal to W1 plus W2. So, it should have an edge and its weight should be less than or equal to W2, W1 plus W2, right. So, that edge exists, right. This edge exists and the weight of this edge should be less than or equal to W1 plus W2, right, by triangular inequality, okay. Fine. So, now I can maybe forget about this path, take this path, again I can repeat that argument, right. Right. I can say that from here to here I have a direct edge, right, because I have this edge and there is another edge of weight W3. So, the direct edge from say this to V3 should have weight less, it should have a direct edge and it should have weight less than or equal to W1 plus W2 plus W3, right, correct. So, if UV is a path, U to V you have a path, then I can extend this property. From this property itself I can say that if you add up all the edge weights on the path between U and V, the direct edge between U and V is of weight less than or equal to sum of the weights of the entire path. You agree? See, I can repeat this now. So, the direct edge, this will have weight less than or equal to W1 plus W2 plus W3. Now, forget about this one, you have this path, so you can go on arguing like this. Then in the end you will conclude that sum of weights of Vi to Vi plus 1 for I varying from 0 to n minus 1, this is greater than or equal to weight of V0 Vn, direct edge, right. So, this is nothing but UV, right. What I just showed you is that if there is a UV path, you sum up the edge weights on that path, its weight is going to be more than, or the sum of the weights is going to be more than or equal to the weight of the direct edge between them. There will be a direct edge and its weight will be less than that path, total weight of that path, right. So, every edge exists. So, between every pair of vertices there is a direct edge, right. So, this graph, if it has metric property, then it is not just any graph, but it is a complete graph, right. So, let us consider a complete graph whose edge weights satisfy triangular inequality. Okay. So, we call, if you want to find a TSP in such a graph, given a graph which, complete graph which satisfies triangular inequality on its edge weights, you, the same problem, find a minimum cost TSP. You do not have to find on every graph, but suppose you have this property, okay. Then can you find? See, distance between places and all these things, if you put in, you have this metric property, distance, okay. So, there are many places where this metric property hold, okay. So, at least let us try to solve the problem, TSP problem, at least approximately on such graphs, okay. So, is it true that for such graphs also the problem is NP complete, TSP problem is NP complete? The problem is this, find a minimum cost TSP on G. So, we are aiming to find an approximation algorithm, two-factor approximation algorithm for this problem. The graph is now a little bit more structured, the weights, okay. So, the first question to ask is, if I put this restriction, then is it polynomial time solvable? Then I need not think about approximation, right? Can you tell me why that is not likely? Can you give me a graph, or not one graph, some reduction from Hamiltonian cycle to TSP such that the resultant instance satisfies metric inequality, metric property, and so if you get an answer for TSP, you get an answer for Ham. We have seen a reduction already like that, just remember. The resultant instance should also satisfy metric property in the reduction. Then only you can say that even for such instances the problem remains NP complete, right. If a reduction, the result of a reduction is always guaranteed to be a graph that satisfies metric property, then only you can say that even for such graphs the problem remains NP complete. Otherwise maybe it is easy for, say, like vertex cover for trees was easy, right, though vertex cover was difficult for some other class. So, the reduction of from some problem to vertex cover cannot result always in a tree. If it always resulted in a tree, you can solve tree and it will imply P is equal to NP, right. So, that is not the case, okay. So, you will get as a result of the reduction some, if it is a restricted class, for that class also the problem should be hard. So, I am now asking you, so to conclude that even the problem remains hard on graph satisfying metric property. So, you give me a reduction from Hamiltonian cycle to TSP such that all the resultant graphs will have metric property. You have seen it, identify, think of it and tell me which among those is the. If for non-edges we put 2 and for edges we put 1, then that is true, right. We always have the smallest one as 1, right, and 1 is less than or equal to 1 plus anything else, right. 2, the biggest one is 2, the smaller two sides can have weight 1 only, right. So, even if the biggest one is 2, the biggest side of the triangle is 2, you do not violate the property because the other two sides, the smallest possible is 1 plus 1, right. So, you can always, in that reduction itself, actually all the triangle inequalities are satisfied. Do not go for higher weights, 1 and 2 is sufficient, okay. So, that means that even for such instances the problem remains NP complete. So our search for approximation algorithm is justified. We do not have a proper polynomial time solution. Let us now try for approximation. Fine. Okay. So this also is like it is a complete graph, remember that. We have that structure anyway. Because we have metric property, it becomes a complete graph. Okay. Cannot be anything else. So we have to find this problem also, we will try to find a related problem and get a bound with that. Okay. So related problem which is polynomial time solvable. So can you think of any other problem which is related to, which may be not exactly, it will not give anyway, some related problem to TSP which is polynomial time solvable. There may be many. Which can give a lower bound to TSP.
Thinking of what spanning tree will help find all the edges visited vertices, but to come back return, we have to think of all.
Let's just delete it, no? Why do you have to have everything?
Spanning tree TSP means we have to come back.
Correct. TSP has to come back.
Minimum spanning tree visit all the things as is usual, but we cannot back.
It may not be a path, minimum spanning tree.
Yeah,
It's
that
a
is
tree.
correct.
All that is fine. But he has some idea, he is trying to relate minimum spanning trees. Minimum spanning tree computation can be done in polynomial time. So can someone help him? Can we say that the cost of a minimum spanning tree in this graph is less than or equal to cost of minimum TSP? Can you help him with that?
BFS or BFS we can use. Spanning tree wala concept.
Spanning tree, you have this Kruskal's algorithm or Prim's,
Prim's algorithm.
right? You can find. But I am not asking you to, okay, we will use it later. We can try to use a spanning tree, but can I have a bound in terms of spanning tree cost for the TSP cost? If I have, then I can relate, right? Try to relate. Finally, I need to bound it, right? It's 2-factor. So can I say that one observation, what I am asking you is it true that the cost of a minimum spanning tree of G, can we say that it is less than or equal to or 2 times this is or half of this? It is less than or equal to cost of minimum cost TSP. Say let me call it as opt. Okay. Opt is the minimum cost TSP of G. Cost of min cost TSP of G. Can I say this? Can I say this? This is easy. Very easy. Very, very easy. Can you find some spanning tree like this? Not necessarily minimum spanning tree. Can you find some spanning tree of cost less than or equal to the cost of TSP? Some spanning tree. You know that there is a TSP tour, then can you find some spanning tree of that graph, of the entire graph, of cost, at most the TSP cost?
Salesperson start from a point and will end at the nth point only. Will not come back.
Okay. So if you delete any edge of the TSP tour, you get a path covering all the vertices, which is a tree, which is a spanning tree, right? So it is easy to get some spanning tree of this graph of cost at most TSP. Some spanning tree, if it has cost less than or equal to TSP, minimum spanning tree will definitely have cost less than or equal to TSP. That's all. So this is true, right? Okay, this is true. So now the question, so we have got a lower bound MST, right? MST of the graph, minimum spanning tree, you know how to find out using Kruskal's algorithm or whatever. In polynomial time we can find out. Now can we find a TSP tour of this graph of cost less than or equal to 2 times the cost of minimum spanning tree? Now you have the target. There is a lower bound. It cannot be minimum cost. TSP cannot be smaller than MST. Can you get less than or equal to 2 MST cost?
You're trying to traverse every edge twice. You're trying to traverse every edge twice.
It gives you a clue. It gives him a clue that suppose you have a MST, you somehow try to traverse every edge twice somehow. He is also talking about DFS, okay? And then if you count every edge twice, you may get 2 times MST, but you have to get a TSP. Every vertex should be visited only once, okay? You are in the right direction. Suppose you know this, okay, I'll help you. So suppose we have a minimum spanning tree. So this is the algorithm. Find a minimum spanning tree T of G. It's a complete graph. Okay. Remember always that it's a complete graph. Find a minimum spanning tree T. Okay. So the tree, it's a tree. It is covering every vertex. No cycles, right? He is telling try to traverse every edge twice. That is something that happens in DFS also, right? So let's try to do something like that. So I will just try to say start from here, go this way. This is a DFS kind of thing, okay? And while coming back, I'll just think that these edges are also there in the graph, multi, okay? And then I will probably traverse this one, right? Go there in the actual edge, come back in this, you will come back, right? So it's like I am just going there, then going here, okay, coming back here, then I go here, then I come back here, this is DFS, right? I again go here, come back here. How did I go? I came like this, went back like this. right? So, the problem here is that some vertices are repeated. If I do it this way, right, I am coming back sometimes several times to something that I have already seen. So, now that, so if I think that I count it like this, so I am counting the cost of this coming back also. What is the total cost? 2 times MST, right? Every edge is traversed exactly twice. Okay. So, now do you have a way to, so you have some path now. So, you are going this way, this, okay, this is yours. You have a circuit now, which is not a Hamiltonian circuit because vertices are repeated. Then how will you manipulate it and get it, convert it into a Hamiltonian circuit? Hmm? Hmm? Minimum spanning tree we have found. Minimum path? From what? Minimum spanning path, I don't have an algorithm also. I don't know how to find. Minimum path I have, the extras algorithm. Minimum spanning path, I don't know. If you have a minimum spanning path, that is Hamiltonian path, right? It is NP complete. Okay, don't think of minimum spanning path. Minimum spanning tree is the right thing. You got a circuit now. I can write down the circuit. Okay. So, if these are my vertices, my circuit is like I start from 1, go to 2, then go to 3, then go to 2, then go to 1 again, then go to 4, then come back to 1, 5, 6, 7, 6, 8, 6, 5, 9, 10, and then 1, right? This is my circuit now. It repeats some vertices. What can I do to make it a Hamiltonian circuit? Hmm? Edges are there in the graph. All edges are, whatever you want, you can add.
We just consider those edges and then we use the metric property. And at max, it can be repeated only 2 times. Any edge which is. So
Why do you want to repeat edges?
No. We find one path. If it ends, if we reach an end vertex, then we will join it to another vertex which has not been visited yet. And then by the metric property.
Correct. Which we had some time back, right? We proved that path is more lengthy than the actual edge, right?
If we consider those extra edges by metric property, each vertex can be repeated at max twice.
Let's do it step by step, okay? He is trying to tell me that there are other edges. This is a complete graph originally, right? There are other edges. So, this is the first vertex that is repeating, right? I just think of this way that I don't want to visit this vertex again because this has already been visited. Instead, what I will do is, okay, so 1 is also visited once, right? I started from there, I have still way to go. So, I don't want to visit 1 also because it has already been visited and it is not the last, okay. So, I will try to go from 3 to 4 directly. I can go because in the graph there is a direct edge, right. So, instead of this way, I will directly go from 3 to 4. So, that is in this graph, instead of taking these two things from here and going like this and all, Okay, I will not go this way, I will directly go here. This edge exists in the graph, right? Okay. Now again 1 is visited, do not take it, I will directly go from 4 to 5. Okay. So, I am not using this edge now. I will go from 4 to 5. Okay. You can draw in your book a separate figure, I am rubbing it off, which you will find difficult at the end. Okay. So, then 5 to 6 I can go, it has not been visited, go the same thing. Then 6 to 7 is okay, this I cannot come. So, 7 to 8 directly I will go, I will not go back to 6, I will go from 7 to 8. Then 6 I cannot go, 5 I cannot go, so 8 to 9 I have to go. So, I will go directly from here to here, I will not go via this. Okay. Then 9 to 10. Okay. Then from 10 I will directly go back, this was not there, okay, right, directly go back to 1. Okay. So, this will be one Hamiltonian cycle that I can construct by short circuiting this earlier circuit that I got, right. So, now I should be careful that when I am short circuiting I am putting some additional edges, right. I should not be increasing the original thing that I wrote here as a circuit. You told me that its cost is at most, it is actually exactly equal to 2 times MST, right, every edge was repeated exactly twice. Okay. The cost of this thing was 2 times MST, equal to 2 times MST. So, this new one in which I am directly jumping like this, it should not increase. I am putting a new edge 3 to 4, 4 to 5, 7 to 8, 8 to 9, right. This kind of edges are newly added. So, by doing this, am I increasing the cost more than that original cost 2 MST? No, because I told you in the beginning itself that by shortcutting a path, you cannot go worse, right. The direct edge will have cost at most that of the path, right. So, this 3 to 4 edge has cost less than or equal to the sum of the costs of these 3 edges, 3 to 2, 2 to 1 and 1 to 4, right. So, you are okay, instead of going this way, if you go this way, it is only going to help us, it is not going to make it bad. Okay. So, by short circuiting, so find an MST T of G. Okay. So, the algorithm goes like this, find an MST T of G, okay. If I have to say this in another language, then I will say double the edges, I got another graph. In this graph, in some sense I am doing an Eulerian tour. It is a DFS tree, whatever, DFS traversal, taking the back edges and all that, or I can also think of it as an Eulerian tour of this new graph, in which edges are, the MST edges are made double, right. In that graph, in that double the edges of T to get some graph T dash. So, this T dash is an Eulerian graph. What is an Eulerian graph? you can start from any place, visit all edges exactly once and come back to the all edges exactly once and come back to the original place. Unlike this Hamiltonian cycle problem, this is a very easy problem. Okay, finding an Eulerian cycle in a graph. Not every vertex, every graph has an Eulerian cycle. What is the condition? You all know it, right? If every vertex has got even degree, then only you can find an Eulerian cycle. This is an if and only if condition. And if there is every vertex is of even degree, you can certainly find an Eulerian cycle. So if I take a tree like this, MST like this, double all edges, you get even degree for every vertex, right? Even if something was odd earlier, on doubling it will become even, right? So that is an Eulerian graph. And you can do an Eulerian traversal on this. That is what exactly, if you just look at what we did initially, that was an Eulerian traversal, right? How to do an Eulerian traversal? You try to go further, don't cut. If you have only one way to come back, don't take that path now, right? Don't go via bridges. If you keep on having that as a rule, you can complete an Eulerian path, Eulerian cycle. So finding an Eulerian circuit is very easy. So double the edges of T dash. So T dash, T to get T dash is an Eulerian graph. Find an Eulerian tour of T dash. It has cost at most 2 times MST. Cost of T dash Eulerian tour is equal to 2 times MST, 2 times the cost of MST. So now short circuit the tour. Without increasing cost. Okay. So that is our 2-factor approximation algorithm. So here again we found one related problem, which is MST. Okay. And we then thought, if we are trying for 2 MST, let's then double the edges and try. Then you found that doubling the edges, we will not get a TSP that easily, but we can get an Eulerian tour very easily. And if you short circuit the Eulerian tour to make sure that no vertex is repeated except the starting vertex which you visit again in the end, then you get a TSP tour, and cost is not more than 2 times the MST. So this is our algorithm. So remember that the general instance of this problem was very hard. We told log n is not possible, n factor is not, nothing is possible. But if you have this restriction that edge weights satisfy metric property, then we got an algorithm which is a 2-factor approximation. It's polynomial time also, right? Because all these steps are MST is polynomial time, Eulerian tour is polynomial, all Eulerian tour or what's he told, it's a DFS traversal in some sense. Everything, all this is polynomial time. So it's a polynomial time algorithm. What's the time? Okay. So let's stop now. Actually, I want to modify this algorithm slightly and make it a 1.5-factor approximation for the same thing, metric TSP. It's a very famous algorithm called Christofides algorithm. What we were saying was that in general TSP problem is very hard to even approximate, but then if we just restrict our attention to only instances where the weights satisfy metric property, then even then we know that it is NP hard, NP complete. But that with that restriction, we have a two-factor approximation where we use the property that using a minimum spanning tree, we know that the cost of a minimum spanning tree is a lower bound to cost of a minimum cost TSP. That was our lower bound, and we somehow from a TSP we got from an MST by doubling the edges and doing a short circuit of the Eulerian tour, we got a TSP of cost at most 2 times that of the MST, right. Okay. So, now we will slightly improve that algorithm to get a 1.5 factor. Okay. It is not like 1.5 MST, okay. That need not be true. Okay. So, MST is one lower bound. So, let us think about some other lower bound for the same thing, TSP. MST is one lower bound which we used. Okay. In addition to that, let us try to use other information also. So, if you have a TSP, minimum TSP or whatever, what other structure can you see in that TSP? I mean, there is some minimum TSP anyway there, right. We do not know how to find, that is okay, but how we related spanning trees to this was like because from a minimum cost TSP, if you delete one edge you get a MST spanning tree. So, MST has cost at most that of TSP. In the same way, from a min cost TSP, can you see some other structures in that min cost TSP tour which is guaranteed to be there, right. What else is there other than this spanning tree? Is there anything else which is also like polynomial time computable some parameter? You have a cycle basically which is covering all the edges. So, what else do you see there? Now, just think, what else do you see there other than a spanning tree? Okay. One more thing. So, why did we go as bad as 2 MST? That is because we doubled every edge to make the graph an Eulerian graph, right. But is that necessary? That is another direction of thinking. So, maybe we can get some other, this MST is there, from that we want to construct another subgraph of the original graph which contains we found an MST T of G. Okay. So, can we find an Eulerian subgraph of G that contains all the edges of T but it does not have everything double. Okay, can we do better? So, we are trying to find an Eulerian subgraph of G that contains all edges of T, but of cost better than 2 times MST of T, MST of G. These two things you can think together. One is like, is there any other structure that you can see in a TSP tour? Another thing is, instead of adding all the edges one more time and short circuiting, suppose you had an Eulerian subgraph that contains this MST, and in addition to the MST, do not add all the edges 2 times, but selectively add some edges so that the graph becomes Eulerian. If you have an Eulerian subgraph that contains all the vertices, then you can do the same technique. Do an Eulerian tour and short circuit, right. Any Eulerian subgraph of G that contains all the vertices, any spanning Eulerian subgraph is sufficient, right. You can do an Eulerian tour and short circuit, and I am trying for 1.5 factor. So, I do not want to double all edges and argue. Okay. So, from spanning tree, if you want to convert it into an Eulerian subgraph of G, what will you do? That is one way to look at it. What can you do? Join in the sense between every one of them, then you are, I mean, you add a click between the odd degree vertices. He is telling, okay, somehow try to make the odd degree vertices even, right. So, how? Add
edges.
So, add some more edges. How many edges should be
There
added?
will be always even number of odd vertices.
Yes, there will be always,
Take pair and join them.
right. Okay. So, in a graph, the number of odd vertices is always even, right, because the total degree is twice the number of edges, right. Odd degree vertices is always even. So, this is a complete graph anyway, right. So, just pair them up somehow, and between odd vertices add some edges, right, one edge, pair them up and add one edge between them. That will make all the vertices even degree, right. Let us look at that graph which we were looking at, that spanning tree. I do not remember what exactly it was, but okay. So, this is a minimum, suppose this is a minimum spanning tree. So, which are the odd degree vertices? This is odd, this is also odd, right. Some places you may see that edge is already present between a pair of them, so such an edge is already present. So, even in that case it is okay, you can double that edge if you want to, okay. There is, everything is possible. So, I am just giving one possibility, double this edge, pair these things up, add this edge, add this edge, add this one. So, everything becomes even degree, right. Okay. So, if I add these dotted edges also, that is all these edges are there in G. So, I can add all of them. So, this is an Eulerian subgraph, right. I can do an Eulerian tour. That Eulerian tour is polytype, okay. Without making any bridge, you keep going. That is the algorithm. But then the problem is, okay, so what can you say about these edges? They have any common endpoints? So, what is that? It is a matching, right. It is not a matching of all the vertices, but it is a matching of odd degree vertices of the spanning tree, right. That is what you added, okay. Now, revisit that question again from your minimum cost spanning tree. So, okay, so what we are adding is some kind of a matching, okay. So, I will write it down, add a matching, I will refine it later. As of now, if we add a matching, actually it is a perfect matching, right, because it is even number, every edge is present. So, if every vertex is matched, then it is called a perfect matching, okay. Between odd degree vertices of the spanning tree, we get an Eulerian graph T dash. It is not a subgraph, some edges may be doubled, okay, but it is okay. Earlier also we did not have a subgraph. T dash that has all vertices of G, okay. So, this graph can you, so how can we construct an Euler Hamiltonian tour of this graph? Similar to what we did earlier, right. So, right, it is not difficult. But there is a problem here that we cannot add any matching, any perfect matching. That is not a good idea because we are trying to minimize the weight, right. So, just not add any perfect matching, but let us add, what can we add? The minimum weight perfect matching, right. This set of odd degree vertices of T, it is a clique actually. If you see the induced subgraph in the complete graph, this is also a clique, right. They have all pairs of vertices between them, right. So, to make things optimal, we will choose a minimum cost perfect matching on odd degree vertices of T. Perfect matching in G. Or if O is the set of odd degree vertices, then in that induced subgraph find a minimum cost perfect matching. So, there are two questions here. One is, is it polynomial time to find this minimum cost perfect matching? Okay. The second question is, then what is the guarantee that we are not adding too much cost by inserting these edges? Earlier we had that shortcutting and we were sure that anyway we were shortcutting a path, right? Now that is not exactly the case now, right? We added some more edges to MST, right? So these two questions we need to answer. So the first question, anyway, I will tell you the answer because it's not, unless I tell you, it's not, you cannot do it fast. So this finding a minimum cost perfect matching can be done in polynomial time. There is an algorithm for that. Minimum cost perfect matching in a complete graph can be found in polynomial time. Okay. Now you assume that such an algorithm exists and let us use that. That is okay. Now the other part is the question. If I add these edges, how much cost am I adding? I already have MST cost taken. All those edges are there. So I don't want, I am aiming for 1.5 times optimum. Okay. This MST is like, it can go as close to this TSP cost, right? We only know one bound that we know is this. MST cost is less than or equal to cost of, let me say cost of T is less than or equal to opt, right? So I need to say that cost of this perfect matching say we will choose a minimum cost perfect matching M in G, okay, G of the induced only the odd degree vertices, okay. So I need to somehow argue that this cost of M, I am aiming for total cost of 1.5 opt. So this should be less than or equal to, I should somehow show that it's less than or equal to 0.5 opt, right? Or in other words, okay. So, okay, now from here onwards, is it true? A minimum cost perfect matching on odd degree vertices of the spanning tree has cost at most half of that of the TSP. So, can we make such a claim? No clue? So if I change the questions slightly, so if I ask you, this is a minimum cost perfect matching in the odd degree vertices, right? Instead, suppose I asked you about the minimum cost perfect matching in the entire complete graph G. Minimum cost perfect matching in G. Can you say that its cost is less than or equal to 0.5 times opt? From the TSP, can you construct some matchings of the entire graph? Do you see any matchings in the cycle? Perfect matching I do not know, because I may have an odd number of vertices, but okay, let us not worry about that. But do you see matchings in a cycle? Any matching? What is a match? I mean, if you are given a cycle, what matchings do you see in that? Kind of, right? Maybe you cannot choose one because it may form an odd cycle. Otherwise, if it was an even cycle, if you choose alternate edges, you get a perfect matching. The other set of alternate edges will give you one more match, right? So that is there, right? Agreed. So I am going to argue that this is true even for this case. Okay. Okay. So can I say this min TSP cost of this subgraph, right, on odd degree vertices of T, this is not greater than min TSP cost of G. Is this true? Is this true? If you are given a min TSP tour of G, can you say that min TSP cost of on the odd degree vertices of the T, or of a subgraph basically, of a subset of vertices is less than or equal to that on the entire graph? Can we say that? It is easy, try. We have all ideas already. If I remove this min, can you construct that? Some TSP tour of the smaller graph, can you construct from a minimum TSP tour of the big graph? Suppose you have a minimum.
Just consider the same tour, and if it's going to an even degree vertex, you just remove that and just join, just directly join the odd degree vertices.
Do you see that? Suppose you have a minimum cost TSP tour on the entire set of vertices. Some are that even degree vertices of T's, others are odd degree. So what he told me is that just short circuit all the even degree vertices. You don't want to visit them. That's it, no? Right? So you get a TSP tour of the odd degree vertices of T by short circuiting. Okay. And by short circuiting, are you increasing the cost? No, right? We are only bypassing one path by an edge. By a metric property, that is only going to help us in the favorable direction, right? So the answer for this is yes. So if C is a min cost TSP tour of G, by short circuiting it, we can construct a TSP tour of this subset of vertices which were odd degree in the tree T, right? So, you got some TSP tour of cost at most, say let us call this constructed TSP tour C dash of cost at most that of C, right. Now, I am talking about minimum TSP tour. So, any TSP tour, if it is already less than or equal to the cost of C, minimum TSP tour of this subset is also going to be less than or equal to this, right. Sum tour, minimum tour, right. Therefore, what I asked is true, min TSP cost of this subgraph, it is also less than or equal to cost of C, which is opt, right. This is opt, the best on the entire graph. So, now I have this G of O, how many, its number of vertices is even number, right. It is a graph with an even number of vertices, GO, right, G of O, and you have found a cycle in it through every vertex. So, now you can find a matching, no. 2 perfect matchings you will see in this cycle, right. Just look at C dash. C dash now looks like these are all those odd degree vertices, something like this, right. Okay. So, these vertices, let us put them there, vertex number 3, 5, 6, 7, 9, 12, 10. These vertices we put there, we get a tour of that, and then you see 2 matchings there, right. Now, we are back to our original thing. So, you see 2 matchings there, right. If you take the lower cost one among them, right, you see 2 matchings here. This is some edges of some M1, this is some edges of some M2, matching 2, second matching, right. Cost of M1 plus M2 is equal to cost of C dash. So, the smaller weight among them is of cost at most. How will you relate it to cost of C dash? By 2, right, and correct. So, since cost of M1 plus cost of M2 is equal to cost of C dash, so we can say that minimum of them is less than or equal to cost of C dash by 2, right, which cost of, this is cost of C dash, right, this is cost of, okay, anyway, cost of C dash is less than or equal to cost of C, that also we can write, right, which is less than which is equal to opt. So, this is equal to cost of C dash by 2 is less than or equal to opt by 2, right. Okay. So, What this means is, okay, so I am not going to add this set of edges because I do not know how to find it out, right. Can I add this M1 or M2 minimum of them to my MST? No. Why? How do I know what it is? If I knew the minimum cost TSP tour of G, then I kind of got it, right? Huh? But I do not know. I mean, I want to find the minimum cost TSP tour of G, right? So, I cannot really know what is this M1 and M2 and to know which is the minimum of them, but I do not need to. What I added, I told you earlier, what did I add? It is a minimum cost perfect matching in G of O, right, which I know how to find in polynomial time. So, this is a perfect matching, right. See, either M1 or M2 is, both are perfect matchings, in GO, at least one of them has cost less than or equal to op by 2, right. I do not know how to find M1 or M2, these things I do not know. But then what I know is, because these are some matchings, this is at least one matching is there of cost at most op by 2. So, I know that the minimum cost perfect matching is of size, is of cost at most op by 2, right. Therefore, this is only a proof, okay. Therefore, minimum cost perfect matching, it may not be M1 or M2, may be something better, right, of G of O has cost less than or equal to op by 2. This is the only thing that we want, okay. So, our algorithm, to summarize it, it is only this. Find an MST T of G, identify the odd degree vertices of T. So, let O be the set of odd degree vertices T in G of O. Find a, all of you know what is G of O, right? G, you discard all the other vertices and the remaining graph, only have these vertices and the edges between them, that is G of O. In G of, it is also a complete graph. In G of O, find a minimum cost perfect matching M. Okay. Then you are constructing a new graph T dash, which is actually the union of T and M. Okay. This is a graph in which, what is the property of this graph? I have taken a MST and between all the odd degree vertices I have added a minimum cost perfect matching. What property does this graph has? It is Eulerian, right? T dash is Eulerian because I added 1 degree for every odd degree vertex. So, find a Eulerian tour of T dash and short circuit it to obtain a Hamiltonian tour or TSP. Of G. So, this is our algorithm. Every step is doable in polynomial time. Finding minimum cost perfect matching is doable in polynomial time. I did not explain you any algorithm, but take it as a black box, it is not. Okay. Now, the other step is finding an Eulerian tour, which you can easily do, even you can program it, even if you do not know much, okay, to construct a Eulerian tour of a Eulerian graph. If a graph has all even degrees vertices connected graph, then you can find an Eulerian tour of that graph, okay, in polynomial time. So, this then you are only short circuiting, which is also like start, and if you are finding a vertex for the second time, skip it. Only the last the first and last vertices can be the same, in between there should be no repeated vertices, that is it, okay. So, you get a tour. What is the total cost? It is, see, this whole thing, cost of T is MST, which is less than or equal to opt. Cost of M is, this is a minimum cost perfect matching, right, it is less than or equal to opt by 2. Right. This was the total cost of T union M. Then you have short circuited. You are doing only better, right. Its cost is not the entire cost of T union M. You do not want to repeat vertices, so you have short circuited, so the cost is only going to reduce, it will not increase, right. So, cost of the tour is less than or equal to cost of T dash, which is equal to which is less than or equal to opt plus opt by 2. So, you got a 1.5 factor approximation for TSP problem, but on instances in which the edge weights satisfy metric property. Otherwise, in the general case, no, nothing can be obtained, no approximation algorithm is possible. Okay. So, here actually if you look at it, we use two lower bounds. One was MST. MST cost is less than or equal to TSP cost, minimum TSP cost. The other lower bound is, if you look at any subgraph on even degree vertices, even number of vertices, right, complete subgraph on an even number of vertices, a minimum cost maximum matching on that is less than or equal to half of opt TSP. So, these two lower bounds together helped us in getting this 1.5 factor approximation. So, this is a very famous algorithm. In the metric case, this is the best known algorithm. This is known as Christofides algorithm.